Hello everyone. In the previous topic we have done what is irrational number, what is real numbers, what are rational numbers. Here in this topic we are going to discuss how to represent rational numbers and irrational numbers in decimal form and the different types of decimal forms. There are three types of decimal forms. One is terminating decimal expansions. Let us see the definition. The terminating decimal expansion means that the decimal representation or expression is terminated after a certain number of digits. For example, when 1 by 16 is expressed in the form decimal, we have 0.0625. Here, the decimal representation is terminated after 4 decimal places. So it is a terminating decimals. Here, the decimal expansion of terminated after 4 decimal. Note, in terminating decimal expansion, you will find that the prime factorization of the denominator has no other factor than 2 and 5. We'll be doing later in later sessions. Now, non-terminating recurring decimals. The non-terminating but repeating decimals or recurring decimals means that although the decimal expression or representation has an infinite number of digits, there is a repetitive pattern to it. For example, when 1 is divided by 7, we have 0.142857, again 142857, and so on. This pattern of digits keep on repeating. That is why we call it non-terminating recurring decimals. Here, let us see how a rational number can be expressed in a decimal form. First of all, let us understand what our rational numbers are. Rational numbers are the numbers that can be expressed in the form of P by Q, where Q not equal to 0, P and Q are co-prime integers. Let us take an example. 9 by 2, which is equal to 4.5. What is this 4.5? 4.5 is nothing but it is in the decimal form. Now, since every rational number can be expressed in the form of P by Q, it can express in the decimal form. So, what is this type of decimal form can it have? Let us see. The decimal forms are: first we have terminating, second we have non-terminating. Let us see some example of terminating decimals form. 0.52, 2.75. Here both the decimal places are n after 2 decimal places, or it may be n after 3 decimal places. If they have ended, then it is called terminating decimals. Let us see, non-terminating decimals are of two types. One is recurring, one is non-recurring. For recurring, example is 0.6666. Here this digit 6 is repeated again and again indefinitely. Let's see one more example of recurring decimals. 2.7777 and so on. Here the digit 7 is repeated again and again, and that is why there are recurring decimal form. Now let us take another example. 8.525252 and so on. Here the digit 52 is repeated again and again indefinitely. Let's take another example of non-terminating recurrings. Seven point 6523232 and so on. Here the digit 2 and 3 are repeated indefinitely, whereas 6, 5 are not repeated, and this is also in the form of non-terminating recurring decimals. Now let us see what are non-terminating non-recurring decimals forms are. Let's take the value of pi. They have no patterns after decimals and never ending. The value of pi, let us take 3.14159 and so on. If you write up to 100 places, whatever 1000 places, there will be no definite patterns of digits are repeated. So they are in the form of non-terminating, non-recurring. Now let us see the value of pi up to 100 decimal places. If you see all the digits of the decimal places, there is no specific patterns in which the digits are repeated. So this is our non-terminating, non-recurring forms, and they cannot be expressed in the form of P by Q. We can also have another example, 6.2030300. Can you see any patterns is repeated? No. Another example is 11.671, 7117, 1117, 1111 and so on. Here 30, another is 300. The next is 3000. In the second form, this 71, 711, 7111, 7111. There's no specific pattern is repeated. So they are in the form of non-terminating, non-recurring decimals. They are always in the form of irrational numbers. Now, non-terminating, non-recurring decimals are always in rational numbers, whereas non-terminating, non-recurring are always in the irrational numbers. Let us see further. Let us see the rational numbers. This is one of the most interesting video based on classification of rational numbers. Rational numbers are always either terminating or non-terminating recurring decimal numbers. We also know that they can express as P divided by Q, where Q not equal to 0. But just by looking at a fraction, can you tell if it's terminating or non-terminating recurring decimal form? Let us see. We look at 6 rational numbers in the form of P by Q. 5 divided by 2, we have another 17 divided by 5, 8 divided by 15, 9 divided by 20, 17 divided by 6, 11 divided by 21, Without calculating the value of each in the decimal form, can you directly tell the category each of them falls into? Either terminating or non-terminating recurring decimal. Let's make 3 rows and analyze it. Let this be row of our number. Just for our understanding, let us calculate the decimal value of each of this row. And we write with the form of each decimal in this row. I mean either this or this. We will write T if it is terminating, and NTR if not non-terminating recurring. Let's try calculating the decimal value of each of the numbers first. Pi by 2 we can write as 2.5. So we can say that it's terminating. So let's write T. The digit after the decimal point ends. Therefore it is terminating and do not go on forever. Let's take another 17 by 5 equal to 3.4, which is also a terminating. So we write T. Let's take 18 by 15, which is equal to 0.5333 and so on. So this is non-terminating recurring. So let's write it NTR. Let's take another 9 by 20, which is equal to 0.45, which is terminating after 2 decimal place. So let's write T. Let's take another 17 by 6. And classify into terminating or non-terminating. Yeah. 17 by 6 is equal to 2.8888, 2.8333 and so on. Here the digit 3 is repeated indefinitely, so it's non-terminating recurring. So we write as T NTR. Let's look the last decimal, 11 by 21, which is equal to 0.523809523809. Here 52389 is repeated again. That is 0.523809 is repeated. It is non-terminating recurring. Imagine trying to do all of this without a calculation. This is how our eyes would look like stunned. Don't worry, there's a quicker way, and we'll need to do is like to do a denominator. Yes, even if we look at the denominator, we can figure out if it is terminating or non-terminating recurrings. So when you see the denominator, the first fraction or the first fraction number is 2. So it is terminating. 5 is also terminating. Next 15 we reduce into denominator into prime factors. We have 3 and 5. Next 20. When you write in the prime factor of 20, we have 2 square into 5. 6, we have 2 into 3. 21 will have 3 into 7. That's all we had to do. Reduce the denominator to its prime factor. Let's observe the denominator of the terminating decimals. The prime factor of the denominators are 2, 5, 2 and 5. Now let's look at the prime factors of the denominators of non-terminating recurring decimals. They have numbers other than 2 and 5. Here we have 3, 3, another is 7. Yes, that's the trick. If the prime factor of the denominator are 2 or 5 or both, then the decimal form of that rational number will be always terminating. If the denominator contains any prime factor other than 2 and 5, then the decimal form will be always terminating, non-terminating recurring, These are the only 2 rules you need to remember. If the decimal is terminating or non-terminating recurring, all we have to do is write the denominator in terms of the prime factors and apply this rule. Let's generalize these 2 rules. If the numbers is in the form of P by Q, then we all need to do or is reduce Q to its prime factors. For terminating decimal, Q will be of the form 2 raised to the power m multiplied by 5 raised to the power n. That is Q equal to 2 to the power m into 5 to the power n, where m and n are integers. It simply means that the prime factor will be either 2 or 5 or both. And how we generalize Q? For non-terminating recurring decimals, is simply we write it as 2 raised to the power m multiplied 5 to the power n multiply k, where k is a prime factor other than 2 or 5 and m and n are integers. It can be 3, it can be 7, or it can be 11, whatever it is. If the denominator contains any prime factor other than 2 or 5, then the decimal will be non-terminating recurring decimals. Now, let us try to solve some of the questions. Let us take the first questions. Without actually performing the long divisions, state whether the following rational numbers will have a terminating decimal expansion or non-terminating decimal expansion. The first one is 13 by 3125, and the second question is 6 by 15, and third question is 15 by 1600. Let's take the first questions. 13 by 3125. According to the theorem, any given rational number of the form p by q, where p and q are co-prime, has a terminating decimal expansion if q is in the form of 2 to the power m into 5 to the power n, where m and n are non-negative integers. So the denominator 3125, when we express in a prime factorization, so we can write in the form of 5 into 5 into 5 into 5 into 5, which is equal to 5 to the power 5. Here the denominator is of the form 2 to the power m into 5 to the power n, where n equal to 5 and m equal to 0. It means that rational numbers 13 by 3125 has a terminating decimal expansion because the denominator can be expressed in the form of 2 to the power m into 5 to the power n. In other words, the denominator has a factor of 2 and 5 only. Let's see the next question again. 16 by 15. Here, what we are going to do is we have to first reduce the given rational number 16 by 15 into simplest form. We have 16 by 15 equal to 2 by 5. Here the denominator is 5. Hence the denominator is in the form of 2 to the power m into 5 to the power n, where n equal to 1 and m equal to 0. It means that the rational number 6 by 15 has the terminating decimal expansions. Now let's take the second question. The following rational numbers will be terminated after how many decimal places? Here what we're going to do is, without actually division, or we are going to determine the given rational numbers are terminated after how many decimal places. So let's take the first question, 23 by 2 to the power 3 into 5 to the power 2. Here what we're going to do is, we're going to make the power of 2 and 5 equal. So let us multiply by 5 by 5. So we have 115 divided by 2 to the power 3 into 5 to the power 3, which is also equal to 115 divided by 1000 will be equal to 0.115. So the given rational number will be terminated after 3 decimal places. In other words, when you see the power of 2 and 5 of the denominator, which one is the highest, you have to see. Here, for example, here 2 to the power 3 into 5 to the power 2. Here 2 to the power 3 is more, so you have to take the highest power, that is 3. Simply we can say that the given rational number will be terminated after 3 decimal places, seeing the highest power of either 2 or 5. Let's see the next question. 15 by 1600. When 1600 is expressed in the form of 2 to the power m into 5 to the power n, we have 15 by 2 to the power 6 into 5 to the power 2. Here also we can see the highest power of 2 and 5 is 6, so that the given rational number will be terminated after 6 decimal places. For your homework, I am giving you 2 questions. The first question is, without actually performing the long division step, whether following rational number will have a terminating decimal expansion or non-terminating decimal expansion. The first, Roman number 1, 35 by 50, and Roman number 2 is 29 by 343. And the second question is, after how many decimal places the following rational number will be terminated? The first question is 17 by 2 to the power 2 into 5 to the power 3, and the third means the second question is 13 by 400. I hope you understand what is terminating decimals and what is non-terminating recurring decimals. Thank you very much.